thing about using formula to communicate is that it creates a particular grammar that we all have to agree upon, right? Just like when we speak any other language, the order in which we say words matters in order to decode the meaning of what's behind a sentence. If we change the order of two words, we can change the order of a sentence, possibly change the meaning of a sentence completely. And so, just as with words and grammar, when we communicate in formulas, we have to know how to extract meaning from the symbols that are there. And we have to know that if you and I both sit down to evaluate a formula, that we're both going to extract the same meaning from that formula. So you and I need to agree upon how we apply the various operations that we see present in this expression. We could, for example, all agree that let's just read the whole thing from left to right and do everything as we see it. Let me put some concrete numbers in here so that we have an example to work with. Let's suppose that I fill this in with, I don't know, 8, 4, 2, 6, 3, 5, 1. No, let's do 1, 5. I don't know. So again, if you want to do this whole problem-solving thing on your own for fun, the goal is to make this quantity as large as possible. So that's the big problem-solving task. But just for the sake of our discussion, let's imagine that we just sort of read everything from left to right and just barreled straight ahead at it. Then the first thing that we see would be this division sign. 8 divided by 4 would give me 2. And then as I came further to the right, I would get this parenthesis, and then 2 plus 6 would give me 8. And then I would have this exponent. I'd have 8 to the power 3. By the way, what is 8 to the power 3? What does that mean? Right, it means to multiply 8 by itself, a total of 3 factors. Remember, it doesn't mean 8 times 3. That's a very easy thing to miss when you're reading an expression, right? That 8 to the power 3 is 8 multiplied by itself a total of 3 times. So that's going to give me, turns out, 512. So then it ends up looking like that. And then I have times 1, which actually doesn't change anything. And then I'm going to subtract 5. This is going to be 1,024 minus 5. This is going to be 1,019. Now, that was what we get if we just read all the operations from left to right here in this expression. But one of the things that we'll find out is that that may not always be the right choice. So don't take this written down here in orange stuff. Don't take that on faith. Because all of us, I was going to say most of us, but it's probably true all of us, have learned a different way of parsing an algebraic expression in the past. Different way of deciding which operations we should do first before which others. And what is that other way, the agreement that we more often make? PEMDAS. Right? It's what's often called the order of operations, or the order of precedence. Right? So PEMDAS gives us a way that we all can agree upon, a way that we can latch onto, that's going to help us all to make the same choices when we interpret the meaning out of a formula. What does the P stand for? Parentheses. And the E? Exponents. Exponents. M and D, I wrote them both on the same line here for a reason. What do they both stand for? Multiplication. Yeah, multiplication and division. And then A and S, addition and subtraction. So that's PEMDAS, and you know, every different math book tries to give you a different, you know, way of remembering what these letters are. Please excuse my dear Aunt Sally and so forth. I like PEMDAS. Interestingly, there's a cultural component to those particular letters. Has anyone ever heard it with different acronym? Out of curiosity, besides PEMDAS? So GEMDAS, so G sometimes, right? Parentheses are sometimes written as G, and those are, what's G stand for? Grouping. Sure. Because then that limits us not just to parentheses, but also things like square root symbols, absolute value signs. There are even fraction bars, our way of grouping multiple things together that don't necessarily have parentheses written on the page, so sometimes GEMDAS instead of PEMDAS. There's also, this is really archaic and bizarre, but I've also seen in British textbooks, brackets, order of, and then MDAS for BODMAS. It all means the same thing, but different, occasionally we'll see it sort of written different ways. But we're going to stick to PEMDAS just because we have to, again, all agree on one way of doing it. And so with that in mind, and I just want to kind of leave this as the frame to which we're going to keep probably returning to understand why this works the way that it works. The reason that PEMDAS in particular is a good choice is that it also honors the ways in which these operations are built off of one another. So addition is the most fundamental of all operations in arithmetic. It's the one thing with which we can't really get off the ground, right? Without which we can't get off the ground. If we know how to add numbers, it turns out that we can do a lot, right? But just adding numbers is not sufficient in and of itself. We also want that operation to have an inverse. Right? And the inverse operation to addition is subtraction. And as we've seen, as we talked about a little bit earlier today, these two operations should really be thought of as the same thing, because every subtraction problem can be made into an addition problem using keep, change, flip. Right? So keep, change, flip is what tells us that these two really should belong on the same rung. That's why I wrote them both side by side here. So PEMDAS doesn't mean that we should do our addition before we do our subtraction. It means that we should do all of our addition and subtraction at the same time. They have the same precedence. And one of the ways of figuring out how to do that is to turn every subtraction into an addition first and just make it all addition. And then we don't have to worry. And the same is true on the next level of the tree, or the little tower here. I call this the hierarchy of arithmetic. If I know how to add numbers, then I also know how to add numbers to themselves, right? And let's say I add 5 plus 5 plus 5 3 times. What's another way to write that addition problem? 5. Well, as an addition problem, it's not cubed. It's, yeah, you're looking ahead. Yes. As an addition problem, or repeated addition problem, we can rewrite it as multiplication, as 5 times 3. So we can use a repetition process of addition to define what it means to multiply, at least what it means to multiply by positive integers. And so multiplication is built on top of addition. Right? It's the next layer on the cake that goes up, right? And multiplication, too, has an inverse, has an opposite operation that can undo whatever multiplication does, namely division. And for the same reason as addition and subtraction are the same kind of operation, multiplication and division are also the same type of operation. Every division can be rewritten as a multiplication. How? Keep, change, flip. Right? So keep, change, flip is what tells us that these two things are really the same. So it's not that multiplication needs to come before division, it's that they should both be put on the same footing, which we can do by turning every division into a multiplication instead. Okay? And so those two belong on the same rung. And then when we take our last step up, there's where we can say, well, we can take something multiplied by itself and rethink of that as an exponent. And so we'll put exponents up here on the top of this layer cake. And as we'll talk more at length about later in the semester, probably toward the end of the course, exponents also have inverses. They're called roots. So the whole point of a root, or a radical, as we'll talk about later on toward the end of the course, is to undo whatever an exponent can do. Right? But it gets a little bit, the story gets a little bit blurrier than it does for multiplication and division, addition, and subtraction. But still, it has an inverse as well, and it belongs on the same rung of precedence, and we can turn every root into an exponent with a keep, change, flip. Right? Just like we did at every other level of this layer cake. And the order of operations as we understand it, PEMDAS, GEMDAS, BODMAS, whatever it is, the order of operations that mathematicians have all agreed upon is an order that takes the higher precedence operations, the ones that are sort of more complex, that are built on top of more layers underneath, and it does them all first. So all your exponents and roots done first. And then once we've done all of those, then we go to the next layer down the cake, do our multiplications and divisions. And then once all of those are done, we move to eat the last layer, the addition and subtraction. So the order of operations is really a way of working from the more complex operations down to the simpler ones. And so addition and subtraction always get left to the end. And so just to wrap up, everything up, if we were to use PEMDAS to evaluate this long expression, what's the first thing we'd do? Parentheses, which means ignore everything outside of those parentheses and just focus on what's inside. Simplify what's on the inside. And so if I did that, the 2 plus 6 on the inside would turn into an 8. And now the quantity on the inside is totally simplified, and so those parentheses or brackets, those are not really serving a function anymore. And so all my parentheses have done their work. If I didn't have those parentheses, this addition here would not happen first. Right? That's the whole point of using them, because if they weren't there, then this exponent and this multiplication and this division would all take place before this addition did. So the purpose of using parentheses is to subvert what would otherwise be the order of operations, right? And make that addition happen before the others do. Now that the parentheses have done their work, what happens next? Exponents. And so we would evaluate 8 to the power 3, which we decided a minute ago was 512. And now I've got division still. I've got a multiplication sign here. What's in between this 4 and this 512? There's a secret multiplication sign. That's another thing we'll get used to more and more as we get into working with algebra, is that if I don't put an arithmetic symbol in between two things, then it's implied that we're multiplying. And then now the question is, what do we do next? Because we have a division, and we also have a multiplication, and another multiplication over here. Here's where things get a little bit weird. You may have seen memes on Facebook where people will put a problem like this up here and say, 99% of people get this wrong, right? And they want you to go click through and take the quiz and find out whether you get it wrong or not. I hate those things, by the way. Those memes, they drive me crazy. And one of the reasons is that the reason this is ambiguous is that most people don't use this division symbol ever anymore, precisely because it causes the confusion that we're about to get into. Remember, keep, change, flip can turn any division sign into a multiplication sign. Keep, change, I'm going to change that division for multiplication. Flip, but my question is, what do I flip? Do I flip just this? Do I flip this? Or do I also maybe include the -5, right? How much do I flip when I keep, change, flip? In this notation, it's ambiguous. And actually, on the webpage that had this problem on it, there was a whole discussion down in the comments with math teachers arguing over this very topic, right? Which is why that division sign is bad news. I'm of the mind that what flips is just this 4. So we flip that into a 1/4. That's the tack I'm going to take just for the sake of us finishing this problem. But I should say, the reason we don't use that weird division symbol with the dots on the bar is because otherwise that's an ambiguous question. So that's why fraction bars are nice, is because they have the built-in grouping property that avoids that ambiguity. But now that we've keep, change, flip so that everything is multiplication, now which of these multiplications do we want to do first? This one, or that one? Turns out it doesn't matter. And so the convention is we'll just kind of do everything from left to right if we can. 8 times 1/4, that's 2, times 512, 1024, times 1, that's all 1024. So when you're doing all operations of the same type, like all multiplication, we just carry those out from left to right as we see them. And that's the only time that left to right really works for us, right? Is when there's only one type of arithmetic to be done. And now that all the multiplication is done, now we'll do the only operation which is left, which is subtraction. We could always keep, change, flip it and think of it as addition of -5 instead, if that helps. But either way we do it, we'll do that operation last. And it turns out that our straightforward left to right approach that we tried to use first actually would give us the same answer as it did here, but there are definitely cases where that is not what happens. So be very careful about left to right. Try to resist that urge, because when people forget the order of operations, that's usually what they go to.